Alright, so in this video we're going to be looking at one of the most, powerful rules that we use in, or tools that we use in calculus. And this is probably going to be, one of the more famous rules, and when people think of calculus, this is probably one of the things that comes to mind, and that's going to be the power rule. The power rule. So we use the power rule as a way or as a tool to speed up that differentiation process, or speed up the process that we use in order to find the derivative of a function. We can only use it for specific types of functions, which I'll get into in a moment, but let me just give you a couple of examples of the power rule in play or in action, and you can tell me that if you can actually just figure out what that rule itself is. Shouldn't be something that is too difficult to figure out. So let's say that we have a function f of x, and that it's equal to x, x cubed. And then its derivative, the derivative of our function f of x, is equal to 3x squared. Let me give you another one. Let's say we have a function f of x that is equal to x to the fifth power. So our f prime of x, the derivative of this function f of x, is equal to 5x to the fourth. Let's say we have a function f of x that is equal to 36, it's equal to x raised to the 36, or let's just say to the 85th power even. We can find this derivative very fast. The derivative of this function is just 85x to the 84th. So hopefully, the pattern here has become apparent. And this is what the power rule is. So to write it out sort of as a formula or more symbolically, we can say that if we're given a function f of x that is some x raised to a power n, then the derivative of that function is simply going to be n times our x raised to the n minus 1. So we can see that happening here, right? X cubed's derivative, we bring the 3, that n, to the front, and we take the power and subtract it by 1. So 3 times x squared, 5 times x to the fourth, and the 85 times x to the 84th. So we can see how this power rule can really make things go a lot faster without having to use that more tedious definition of the derivative that we've been using so far, or up until now. So let's look at a couple more examples of the power rule in action. So again, feel free to pause the video and approach these problems yourselves. There's no need to just watch. You learn by doing. So let's say we're given a function y is equal to 1 over x. Can we use the power rule to solve this? At first, it may appear that we can't, right? We're told that the power rule can be applied for functions that are in a form looking something like this, and there is no exponent here. But if you realize that this is a fraction and that we can actually rewrite this function here in another form, that we can rewrite this to look something like this, x to the negative 1. These two are actually equivalent, right? If you remember back to some of our rules from algebra and pre-calculus, we know that x raised to the negative 1 is just equal to 1 over x raised to the first power, and x raised to the first power is just x. So we're able to rewrite our function in this way, and then now we can comfortably use our power rule. So let's go on to differentiate this function. Again, we can write this as dy dx. For the derivative, we can also just simply write y prime to show that this is the derivative. But basically what we have to do is just we bring that negative 1 over here, negative 1 times x raised to the negative 1 minus 1, which is negative 2. And this is something that we can further simplify, right? We can rewrite this in a more clear form, something looking more like this. So what we can do then, again, we know that x to the negative 2 is just 1 over x squared. So this gives us an answer. Our derivative here is just negative 1 over x squared. And this is going to be the answer. This is the derivative for this function here. So, all right, let's look at another example. Let's say that we're told that we have a function f of x, our function f of x, which is equal to 1 over x to the fifth. Can you try to find the derivative of this function using the power rule? So the first step again is going to be to rewrite this function in a form that's more compatible with the power rule. So we can rewrite this to look something like x to the negative fifth. This is, again, these two are equivalent. So now that we have it in a form that we can use the power rule for, let's take the derivative. Our f prime of x, differentiating this function, gives us negative 5 times x to the negative 6, right? It's negative 5 minus 1. This again is something that we can simplify. We can rewrite it to look more like our original function here. We can do that by, just give me a second. So we can rewrite this to look like in the fractional form again, right? This is negative 5 is going to, or if we want to rewrite it like this, just to make it clear for clarity purposes in the beginning. So we have our negative 5 times x to the negative 6th can be written as 1 over x to the 6th, right? So then this, multiplying this out, gives us an answer of negative 5 over x to the 6th. So this is then going to be the derivative for this function here. So we can see the power rule really does make things go a lot faster. If imagine having to use that definition of derivative, mechanism over here, it would clearly just take a lot more time to get done. So this really does expedite the process. So now let's look at a couple more functions here that we can rewrite, or that may initially seem incompatible with the power rule, but after a little closer examination, we can see that we can actually use the power rule here. One of these functions is going to be this one right here. Y is equal to the square root of x. Again, here, this doesn't look like it's an exponent, right? This isn't an exponent, but we can rewrite this function. We know that the square root of x can just be written as x raised to the 1/2 power. Hopefully this is just a review for you guys. It isn't something you're seeing for the first time. If this is causing you a little trouble, I recommend going back and reviewing some of these sort of ways that we can rewrite different functions and different functions in their different forms, as it's going to be very useful here, as we can take something that we may not use a different mechanism for and then end up writing it in a form where we can just simply use the power rule. So that's just a tool that'll really make things go a lot faster and make your life a lot easier. So anyway, so now that we have this function in this form that we can deal with, let's just take the derivative. The differentiating this gives us y prime is equal to 1/2 times x raised to the 1/2 minus 1, right? So that's 1/2 minus 1. Remember, 1 can just be written as 2 over 2, right? And this gives us negative 1/2. So we can then raise this x to a negative 1/2. So this is something, again, we can further simplify. How can we do that? Well, just for clarity purposes, let's write it all out again. 1/2 times x to the negative 1/2. That would be 1 over the square root of x, right? So then simplifying this, or multiplying this out rather, gives us 1 over 2 times the square root of x. This is going to be our derivative. Alright, hopefully, again, this is making some sense. Nothing that is too challenging here, just may take a bit of getting used to in terms of converting and then just using that power rule. I promise the more you use it, it'll just become muscle memory and you can pick up on these things very fast. So let's look at another example here. Instead of y, let's just say again f of x this time. Again, it's the same thing and there's no difference here. But let's say that our f of x is equal to the 5th root of x cubed. How can we use the power rule to solve this? So firstly, we start again as usual by writing it in a form that where we can use the power rule. So our function f of x here can be rewritten, right? We know that the cube root, or not the cube root, the square root is x to the 1/2. This is the square root of x. X raised to the 1/3 is the cube root of x. So similarly, x raised to the 1/5 is going to be the 5th root of x. So that covers that part of it. But what about the x cubed? So if you remember that if we have a exponent inside of a square root there, that would just end up being the numerator of the fraction. So what I mean by that is this would end up being written as x to the 3/5 power. So x raised to the power of 3/5 is the same thing as the 5th root of x cubed. So here we have our function. We can go on to differentiate it, giving our f prime of x. We bring the 3/5 to the front, 3/5 times x raised to the 3/5 minus 1. This seems to be glitching momentarily again. Let's see. Minus 1. So in order to evaluate this a bit easily, we have to basically write 1 as just 5/5, right? 5/5 is the same thing as 1, so we're dealing with a common denominator here. We can more easily do the subtraction, giving us an answer of negative 2/5, right? So that's going to be our exponent here. So we are raising our x to the negative 2/5. So now, again, we can further simplify this. So our f prime of x is 3/5 times x raised to the negative 2/5. The 5th in the denominator tells us that we're having a cube root. Or firstly, we see that we have a negative, which means that this is going to be 1 over something. So we know that this is going to be a 5th root because we have a 5 in the denominator. So something, we're taking the 5th root of something. And so this is x to the 2nd. So as we saw previously, this is just going to be the 5th root of x squared. So then further, going on with this multiplication gives us an answer of 3 divided by 5 times the 5th root of x squared. And this is going to be our derivative. These things seem to be getting a bit more and more complex here, but just take it step by step. Remember all the tools and tricks that you've picked up over the years in your algebra and pre-calculus classes, and you should be fine. Just make sure you're keeping track of everything. So if you feel like you need to write everything out in this way, be sure to do so. It's better to take a little longer but get the right answer than try to do it really fast and mess things up there. So this is going to be the answer for our derivative here. So let's look at one more slightly more tricky example where we actually have to also do some substitution at the end. It shouldn't be anything too crazy again here. Just keep your algebra in mind and you should be okay. Let's say we're given a function f of x that is equal to the cube root of x times x cubed. And we want to evaluate this and find the derivative of 8 here. So we basically want to find the slope of this function when our x value is 8 is what we have to interpret this as. So we're trying to find f prime of 8. So first we have to find f prime, right? Let's find the expression for our derivative into which we then substitute 8. So we start this problem just as we would with any other problem where we're trying to use the power rule. So we can first rewrite each of these in a form that the power rule can accommodate. So the cube root of x. So our function f of x is going to be equal to x to the 1/3 times x to the 3rd is already in a form that we can deal with. So x to the 3rd. So how do we deal with multiplying exponents, right? If you recall that if we have exponents that where we're multiplying things together here, that basically means that we have to add them, right? We end up adding 1/3 and 3 in order to get our answer here. So that's just going to be 1/3 plus 3 can be written, if we want to use a common denominator again, right? 3 is equal to just 9/3, right? If we're writing it in this form, 3 is just 9/3. So that's going to be 1 over 3. 1 plus 3 plus x to the 1/3 plus 9/3, which is going to give us x to the 10/3. So this is our function. This same function, it can be rewritten as x to the 10/3. So now we have to take the derivative of this. Differentiating using the power rule shouldn't be too difficult here, right? We bring the 10/3 to the front times x, and now we just take 10/3 minus 1. Again, using a common denominator, 1 would just be 3 over 3, giving us an answer of 7/3. 7/3. So we're raising here our x to the 7/3 power. So this is going to be our answer here for our f prime of x, but we can go on to simplify this, right? We can rewrite this in a more neat form. Remember, this is just going to be 10/3 times the denominator being a 3 tells us that it's a cube root, and here the numerator being a 7 tells us that our x is raised to the 7th power here. So this is going to be what we're looking at right here. So because, again, we can also rewrite this, slightly more, just writing 10, if we want to just distribute, multiplying that fraction out, 10 times the cube root of x to the 7th divided by 3. Again, that's, if you want to do that, feel free to do that. But since we are also just here looking not exactly for the derivative, but we're looking for the answer, what is f prime of 8? That's the answer we're looking for. So we can leave it like this if we so choose, and just write 10/3 times the cube root of 8 to the 7th. We're substituting our 8 into our expression for the derivative. And if we do that, we'll get an answer. Again, if you want to plug this into your calculator, you'll get an answer of 1280 divided by 3. This is going to be our answer. This is our slope for our function at x equals 8. So hopefully, everything here has made some sense. That brings us to the end of the video. The power rule clearly is a very useful tool, so make sure to use it whenever you can. Always observe and try to notice patterns in the functions that you're given. See if you can rewrite them in ways that'll make your life a lot easier, and you can use tools like the power rule to do that. In the future videos, we'll be looking at more tools like this to make differentiation and derivatives go a lot more quickly, so be on the lookout for that. But in the meantime, again, please show your support by liking and subscribing. Leave any questions in the comments that you may have, and I'll see you in the next video.